So let's start. So today is we are going to talk about Atiyah-Hodge theorem. And actually, in no Hodge theory book, it is called Atiyah-Hodge theorem because always the people start with Grothendieck. And this theorem is a kind of assumed to be true. And if you look at the Atiyah-Hodge theorem, actually you don't find it, but a lot of computations that we need in the proof, it's in the article. Okay, so let me start. Just a moment. I have to. Oh, no, actually, let's do the notation. U affine variety. And maybe today I'm going to give the idea of the proof of Atiyah-Hodge theorem. But before this one, let me say what is my main example. Remember that we had, let's say, in Pn plus 1, we had the hypersurfaces given x by f equal to 0. Let's call it the f capital F. And f was a homogeneous polynomial of degree d. We assume that x intersect this Pn at infinity transversely. So this is a transversal intersection, and it resulted that if this Pn is given by let's say x0 equal to 0, then and maybe if my chart is x0, x1, xn plus 1, then I will have my Pn plus 1 will be just this Cn plus 1 union y with this Pn, and here I will use coordinate x1, x2, xn plus 1. And if I do f equal to f, x0 equal to 1, and then x1, x2, xn, then the transversality that we were talking will be translated into this statement if we will write the homogeneous pieces of f, this small f, then fd minus 1 plus fd. And then this is, let's call this, so this is fd is the last homogeneous piece of f. Then the transversality is translated into this fact that this dimension of c x will be, x for me will be this one from now on, divided by Jacobian of G. This is a finite dimensional vector space. And the Jacobian ideal is just the partial derivatives of G. And so my main affine variety is given by this f equal to 0 inside Cn plus 1. And actually, after the proof of Atiyah-Hodge theorem, I will mention a more refined version of Atiyah-Hodge theorem using Brieskorn modules. So let's go on. So last time I mentioned that the first idea is that okay. So maybe from now on I choose the notation of that I have used in the proof of the Atiyah-Hodge theorem. So from now on, x will be this f equal to 0, and now x bar will be its let's call x tilde will be this f, the projectivization of this one, which in this let me say in this way, actually now x tilde will be our original x here. So this is just a change of notation because in the proof this new notation is used in my book with Roberto. So this will be inside Pn plus 1. Okay. Okay, so the point is that, and this is already smooth. This is already smooth. But in general, if I take with X affine, let's say it is inside some Cn, then I projectivize it and I compactify it. X tilde inside, let's say Pn. So let's say this inside E. So this X will be affine subset of this projective variety, but X tilde in general is not smooth. And then there is this, I recall that Hironaka's desingularization. So X itself is smooth, but X tilde might not. But at the end of the day, one reach to this kind of diagram. So this is X bar is the Hironaka desingularization, the theorem, and let's say X bar minus X is normal crossing divisor. Okay, so in our main example, we don't need to make a desingularization, because in our main example, X bar minus X is just this. Let's say this X bar intersected with this Pn, the projective space at infinity, and this is already smooth. So in our main example, we don't need. But the one remark that in my book I have generalized to this one, to this tame polynomial, in which I put weights for the variables. And in that context, still one needs to make the desingularization. But for this this class of tame polynomials, we don't need to desingularize. Okay, something nonsense I told last time. One of you remarked me. So what was this normal crossing divisor? So at the end, let's say this I have X. This is X. Let's call this one D, denoting for divisor. So at each point of the desingularization, if I take charts here, U with holomorphic coordinate system, Z1, Z2, Zn, then we will have what? Then let's say X bar tilde near to this point. This is usual topology. This means a small neighborhood of X bar around P. A small neighborhood. Then this will be just the union of Zi equal to 0 for a bunch of variable, I equal to 1, for example, until R. Okay, and as I said, these are the coordinate system. So in some sense, this means that all these components, if we write D intersected with D at the union of di's, then all these di's intersect each other transversely and so on. Anyway, this is the first big theorem that one uses in the proof, and this is the one reason Hironaka proved his theorem after the work of Atiyah-Hodge. That's why the full proof of the Atiyah-Hodge theorem were established later, not really in the Atiyah-Hodge article. But anyway, so let's go further. So first we do this one, and as I said, in our main example that at the end we will be back, we don't need to make desingularization. We just make this classical projectivization, and f equal to 0 by our hypothesis will intersect the infinity transversely, and this we will have this. This will be just this point in the picture. Okay, but we are going to try to prove, to give the idea of the proof in general. So the next step. So let me say, I'm following section 4.3. I'm our book with well, my text with Villa Fleur. So this is one point. Maybe the next step. Oh, okay. So the next step in the proof is that whenever we consider so this is, let's say, x bar, complement is x, and this is my d. So whenever we consider algebraic differential forms in x, in x or in an open set, okay, let's say in x, then something that you have to observe, something that you have to observe, these are automatically algebraic differential forms in x bar with poles along D. I mean, this is a kind of immediate that in algebraic geometry, whenever you are using polynomials, at the end, when you do any kind of compactification of your ambient space, your algebraic objects are always meromorphic along the divisor of the compactification. And if you have in the same way, for example, if let's say f polynomial, f, maybe a polynomial of degree d in x1, x2, xn, let's say it's n plus 1, xn in Cn plus 1. But you can see this one as a meromorphic function in P n plus 1 with poles of order D along the compactification, the Pn plus 1 minus the Cn plus 1, which is Pn. This is just f. This is just the process of the homogenization. If you take then the whole f x1, x0, xn plus 1, x0, and you see that if you do this homogenization, then at the end the x0 to the d will come in the denominator. Anyway, this is one first step here. And okay, then what is the next step? So this is still in the category of algebraic object, but we can consider, let me say, so what is written in the book is G star is notation omega p x over c. So maybe this is well, this is sheaf in the whole x bar, and its section, its sections just come, let's say, I will consider its sections in let's say x bar, the u Zariski or usual. No, actually, in this case, the Zariski, this Zariski open. What is its section over U? It will be just the sections of omega p, just algebraic differential forms section in U. So U intersected with X. Anyway, this notation means that at the end I will consider algebraic differential forms outside, and then for sudden I will consider them as sections of my new sheaf over the whole U. Okay, this is just a matter of a question, but what I need, the reason that I introduced this one, omega p x analytics. Now I put the whole x bar analytic, the sheaf. Maybe I put also star here, star D, the sheaf of meromorphic P form. So whenever I put analytic, I am in the holomorphic context. P form in X pair with poles of arbitrary order along D. Anyway, what I am saying, maybe I write also this one and then a little bit explain more. So I need this inclusion, omega px c algebraic differential form which are automatic, automatically meromorphic along C. They are inside this omega x bar and P, let's say star D. So any algebraic differential form on X will be automatically meromorphic along the divisor D. This will this is automatically holomorphic, and I can consider in the holomorphic category. Okay, so maybe why I introduce this one? Because I want to get, the idea is that to get rid of the Zariski topology in order to prove Atiyah-Hodge theorem. Maybe again one big theorem that one needs Sir Gaga. I just write it. The global sections of this guy you remember that this is affine. This is first of all, this is a definition by definition. This is just omega x, and this is just a note, actually just notation. So this is just a definition of this guy, is just this one. But what is the Gaga's principle? Global algebraic differential forms over X is the same as, maybe then this one here I have to put X bar, is the same as the holomorphic okay, maybe I say in this way. Global differential meromorphic forms in X bar with poles along D in the holomorphic context, they are necessarily algebraic. So here we have this inclusion. This inclusion is trivial, but the point is that why suddenly a holomorphic section, a holomorphic differential form becomes holomorphic, it is a part of this Serre-Gaga theorem. Here the fact that X bar is projective, we use this. For example, of course, this is not true if X bar is affine. For example, in C we have holomorphic functions which are not at all polynomial, and so anyway, the moral of the story is that our compact, our projective varieties, global sections of the coherent shifts, they come from if the coherent shift is the, let's say, the analytification of some algebraic shift, the global sections they are already algebraic. And okay, so maybe
just a question. So, but this theorem is actually true for any coherent shift?
Yeah, exactly. This is just a consequence of the Gaga. As I said, if somebody wants to give some talk about Gaga principle, it would be very nice. This is actually, you have coherent shift algebraic. If you have a algebraic coherent shift, you out of this one, you can contrast a coherent shift which is analytic.
Yeah, okay. And then the global section.
Both of them are a projective variety X bar. Then this the theorem. Again, a part of the theorem says that the global sections of this analytic shift, they are just again algebraic. In our case, our algebraic shift is that this P form, which were algebraic P forms with poles along this T, and this its analytification. Of course, it is the shift of a holomorphic P form.
But in this case, you just need X bar to be projective, like so.
X bar must be projective, exactly.
But does it need to be the resolution, like, or can it be singular, or does it need to be smooth?
No. In Gaga said the things can be singular. Here we don't use the X bar as a smooth.
Okay.
The smoothness we will use in the later in the proof of the Atiyah-Hodge theorem.
Okay, perfect. Thank you.
But as I said, if somebody wants to contribute to the course and to give a kind of contribution, that would be good. And as you see that we are already in the 11th lecture, and I have still not defined, let's say, what's Hodge cycle. And I think at the end. Anyway, let's go. So then the next step of the proof. So, and anyway, in the proof of the Atiyah-Hodge theorem, then I don't need to consider Zariski topology, and this is the main part. I need only I return back to this analytic object and usual topology. So you remember that in the Atiyah-Hodge theorem, I use this guy to define to write down one side of the isomorphism. Anyway, so let's go further. There is another big theorem coming on. Unfortunately, I will just use these theorems. That's Kodaira's vanishing theorem. And the Kodaira vanishing theorem. Let me just write down in our context. All these cohomologies, omega p X bar, and from now on, just forget the Zariski topology. We are just working with usual cohomology. So all these cohomologies are zero, and here we we use the fact that D is an ample divisor, and from where it comes that D is an ample divisor, the fact that this x bar minus x is affine. Anyway, this is another part of the theorem. You see that so far we have in order to prove Atiyah-Hodge theorem, we have used three big theorem, and almost all of these theorems are done after Atiyah-Hodge. Okay, so we have these cohomologies are 0 also, but according to let me write down in this way. But remember that we have also this this complex omega 0 x bar and star with the derivation, and so we have this complex. Maybe I write it. Let put partial d omega 1 expand. Too much notation going on, but okay. And since we have this, all these things are 0, what it means that we have actually a cyclic complex. This means that if I take hypercohomology of this guy, omega bullet x bar and poles along then this is just the global section. So this means that at the end this is the hypercohomology. Cohomology.
We can see.
Oh, sorry. Okay. Okay. So since these cohomologies are 0, if I take hypercohomology of this one, last time in 2 examples we saw that this is HP, taking the global sections and taking kernel to the image, to the bullet x bar and star d. In the book I have put y and then this. Okay, so what is this? Then you take this global sections, let's say the complex of global meromorphic forms in D, in x bar with poles along D, and then you have the differential, and then you take the kernel divided by image. So the hypercohomology is turns out to be again like classical de Rham cohomology, some exact closed global M4 divided by exact global M4. Okay, so this is one step. Okay, so now we are almost the main content of the prep. We are almost done. So maybe let's write down this inclusion I. So we have x bar and poles along D. Maybe I write it and then I explain it. Okay. So let's. I remember again what we are doing. Okay. So far I talked about this complex. So I have the here when I write bullets the complex, and I need also this complex in a similar way as the other one that I introduced, G star. You just consider let's say C infinity forms over X, okay, Okay, of course, C infinity form, you cannot extend it to the whole X bar. But you define again a new sheaf on, let's say, on X bar. This is a sheaf on X bar. What is this sheaf? The sections of this sheaf over U, let's say, G star, for a small, let's consider just for a small P X infinity, the section of this guy over U, they are just the C infinity forms in U intersected with X, just in this. It's a kind of sheaf theoretical extension of a sheaf to D, and actually you don't extend in the well, in analysis way. Anyway, okay. Once again, if I have a meromorphic differential form with poles along T, they are already C infinity. And okay. So something that it is not really difficult if you have well, first of all, this is a kind of morphism of complexes. So something that it comes directly from the definition. If you have this morphism of complexes, at the, then when you take hypercohomology in both sides, then you will have again a map. This sheaf and this sheaf, all these sheaves they do not have, they are acyclic. Remember, right now I showed that this is isomorphic to, let's say kernel, global section, image, global section, and the sheaves are coming from here. And in the same way, here we have the same thing. This will be the classical HP theorem X infinity, the classical. And my theorem, the Atiyah-Hodge theorem, is basically says that since I have already proved that these guys, this will be algebraic. Remember that here is still we are working with the sheaf of holomorphic functions, but at the end these are algebraic. What I have to show that the map induced by this map is an isomorphism, and this will finish the proof of the Atiyah-Hodge theorem. Here, it's infinite differential form. Here, holomorphic global meromorphic forms. But using Gaga, they will turn out to be algebraic. And let me. And here we land on another concept in sheaf cohomology. I is maybe, in order to make this, let's go. When I take the hypercohomology, let's call it Let me see what I have to do. HQ, that actually HPI. I is a quasi-isomorphism. So the rest of my lecture, I will just try to explain what is a quasi-isomorphism. Isomorphism. And okay, so maybe in order to get her rid of this heavy notation, so let me say, I have a complex. Let's use simpler notations of a complex of abelian sheaves. And I have a morphism between this one and, let's say, S tilde I. In our context, this. And remember that again, what is a morphism between two complex? Let's say S1, S2, S3. Let's say we have D, we have D, and then S bar tilde 1, S2 tilde, SD3 tilde, blah, 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 and then here goes on also. So a morphism between two complexes will be just a map from here to here, such that everything commute. Okay, this is the situation that I have upstairs. And what is I? So is a quasi-isomorphism if induces the local isomorphism. Okay, so let's explain. The point is that here, local around point, you can take the kernel of D divided by the image of D. In the same way, you can here take around the point, you can take kernel divided by D, and then we will have induced map, and this must be isomorphism. Let's try to write it. So here I will use the stock. Let it write down. Okay, so SP sheaves for sheaves, let's say for all sheaves in the ambient space. So let's say all of these sheaves are over let's say X space. So from now on, I use another notation. So X will be the ambient space of the both complex S and the S bar. So if I take the germs of sections of S around X, then I will have an abelian group. Then I can take this kernel, and I can kind of form a local cohomology. Then SP minus 1 sheaves, SP sheaves. And by the fact that this I is a morphism of complexes, then you will have this map. So you have this map, let's say I at sheaves, in the same way you do it in kernel, SP sheaves tilde, SP plus 1 tilde sheaves divided by image SD tilde P minus 1 sheaves SD sheaves. Anyway, if you have a morphism, then you locally will have these maps, and if the induced maps, all these the quasi-isomorphism is the one that all these are isomorphisms. So morphism between two complexes of abelian groups on a manifold X is isomorphism. If you form the cohomologies locally around points, then you will have to get an isomorphism. And yeah. And okay, so before so maybe I sketch. So what we want to do, we want to show that this morphism that we had here is a quasi-isomorphism, and then we will use a kind of a simple proposition. Quasi-isomorphism of complexes induces isomorphism when you take hypercohomology. Maybe then I write this theorem and then we'll go. Proposition. Again, this proposition is not simple. Any quasi-isomorphism between two complexes of abelian group induces, when you take the hypercohomology, here I am simplifying my note. If you take hypercohomology, isomorphism. Okay, again, this proposition is not difficult. It is just really the direct consequence of the definition of quasi-isomorphism and the definition of the hypercohomology that we have done. So maybe since I'm going to tell the idea of the proof, just remind in mind that if you have a quasi-isomorphism of complexes, then in the hypercohomology they will be isomorphism. Now we are almost reaching to the trivial part of the Atiyah-Hodge theorem. Okay, so let's return back to the main example. I had this morphisms of complexes, analytic objects, C-infinity objects with the same usual topology of X bar. What I wanted to show that the map induced in hypercohomology, it's isomorphism, and this was finishing the Atiyah-Hodge theorem, because when I take hypercohomology here, I get global sections, and here taking global hypercohomology, I was getting the classical de Rham cohomology. And okay, so I want to show that in hypercohomology they are isomorphism. According to the proposition that I wrote you, what I have to prove, I have to show that this map is a quasi-isomorphism. And this is what we are going to do in the next few minutes. So I have to show that this is a quasi-isomorphism. And remember that quasi-isomorphism is completely a local statement. And okay, so final step in the Atiyah-Hodge theorem. So the final step is, maybe I write the complex of meromorphic forms in X bar, analytic with arbitrary poles along D. This is there is a map inclusion from meromorphic C-infinity forms. Maybe actually, if I want to write the notation, then there was this G star which was taken into 6, so this will be just X infinity. Okay, I had this. I don't write the differentials are the usual differentials of differential forms. Okay, so this is a quasi isomorphism. I'm writing F. Okay, and this is now just a kind of complex analysis. Let me explain a little bit this one. I was planning to talk about Brieskorn modules, but maybe in another lecture I will talk about Brieskorn modules. Okay, so again, just write down what is the definition of the quasi-isomorphism. Remember that quasi-isomorphism is just a property locally. So this means that at the end I have to choose points, let's say P, and or let's call it X. And remember that my divisor D Well, if x is not in D, then just take a small neighborhood. But if x is in D, remember that at the end there is a neighborhood U. Let's say U of x such that U intersected with x bar is given by Z1 equal to 0. There are holomorphic coordinate system, blah, 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 blah. ZR equal to 0. And so what I have to show, and then what this means, I can assume that U is let's say what I'm saying. U is isomorphic to, let's say, polydisk D N. Let me say that disk, this is the usual disk of a radius, let's say epsilon, whatever. And at the end of the day, I have these coordinates here, Z1, Z2, Zn. And what else? Yeah. And then what is my D? This D will be just the union of Z1 equal to 0, ZR equal to 0. Anyway, since the quasi-isomorphism is a local property, I just forget this global context of X bar, and then I just focus on this small neighborhood, which is a disk. So what is the quasi-isomorphism? We have to prove that. So let me just write down. Okay, so we have to prove that. Let's say from one side, I have this, let's say, usual de Rham cohomology of this polydisk minus D minus some coordinates equal to 0. And from another side, what I have the holomorphic ones. Let me write, maybe let me write HP. Let me write it in words, not with notations. Then meromorphic P meromorphic closed P forms with poles along what? Along, then it will be Z1 equal to 0. Sorry, I made them kind of along Z1 equal to 0, ZR equal to 0, and then divided by exact one, exact meromorphic exact P form, blah, 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 blah. So you see that the quasi-isomorphism, I statement the quasi-isomorphism, it's a kind of the similar Atiyah-Hodge theorem, but in purely local context of polydisk, and taking out Z1 equal to 0, ZR equal to 0. And the fact that here Z1, ZR are coordinate system will be essential in the proof of this statement, and this comes from the fact that this original D was normal crossing. So if I want to make a proper notation, maybe just the D was the global object. Maybe I better not write. It was Z1 equal to 0 union with Z are equal to 0. Anyway, and so this is the complex analysis. Maybe in order to say that really this is a simple statement. For example, if it doesn't intersect, maybe I just consider two cases. Maybe let me. Okay, let me just talk on top of this. For example, when this x does not lie in D, then x is something like outside x. So there is no this set. But we know that the cohomology of the polydisk is 0 except in dimension 0. In the same way, in the same way, also we know that this guy is 0. In any way, this means that in a polydisk, a holomorphic closed P form is always exact also. So one gets 0 and then the things is trivially proved. And maybe in another interesting case would be maybe, for example, if you put n equal to 1 and r equal to 1. Here you see that you will be disk minus a point. Disk minus point, we know its cohomology. It's generated by one element, but this one element is already meromorphic. It is generated by dz over z. But anyway, let me write in general. So one has to prove that this has a basis. Maybe I just write down it's the format of its basis. In the non-trivial case, maybe let me say Q between R. The other cases are really trivial, and I don't want to get worried. For example, when Q is between 1 and R, this guy is actually has a basis which are coming from here. This is, has a basis. So let me write the basis. So the basis is dzi1, dzi2, dziq. We are allowed to take division over zi1, ziq. Yeah, and so one has to show that this theorem cohomology defined by C infinity forms is generated by these things here. 1 I1 less than I2 blah, 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 IQ, and IQ is less than equal to R. Okay, so for this problem, you can forget all this shift theoretical problem. You have to show that this classical de Rham cohomology has this basis here. In the same way, this quotient also has this basis. And at the end, you are lead to that to show that this is an isomorphism. So maybe once again, after all these blah 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 of shift theory, quasi-isomorphism, I don't know, Kodaira, Hironaka, and so on, we are reduced to prove that polydisk minus some coordinate is equal to 0. Its cohomology, its de Rham cohomology is given by meromorphic objects. And we just need to consider a meromorphic differential form. This is a kind of, let's say, affine variety minus, let's say, well, the analytic local version of the Atiyah-Hodge theorem. Okay, maybe just 5 minutes. So it's a kind of, well, a theorem that how it is good to carry in mind the rigorous idea of the proof, because one learns a lot of other theorems. If you have questions, we can do it. And again, let me return back to my to my main example. For my main example, maybe I just show you one page of my book. Discard and then finish. Okay, for my main example, which I in my book I put it in the more tame polynomial context. One can even write down explicitly the basis of the de Rham cohomology of this affine variety given by f equal to 0. And for this one, maybe just I say a few words. Because I'm not sure that soon I will be able to talk about this topic. Okay, so in this context, something which is very nice to do, one generalize this de Rham cohomology to something called Brieskorn module. Anyway, it's a little bit some finer version of de Rham cohomology, but okay, after doing a lot of algebra, because we are just using algebraic differential forms and so on, taking Cohen-Macaulay rings, blah blah blah, and a lot of things which are of algebraic nature. Maybe I have to say, just I wanted to mention the main theorem. Okay, maybe this maybe okay. So this one defines something like this Brieskorn module, and this is exactly the the version of the de Rham cohomology of f equal to 0. So the idea is that we want to capture the cohomology of f equal to 0. And the Brieskorn module H prime is a kind of substitution for this de Rham cohomology. Maybe after introducing Hodge filtration and so on, I will be back to this one. But what I wanted to say, that in this case, one can write down explicitly a basis of this de Rham cohomology, because and this basis is given in this theorem. Remember that in the homological part, we are interested to write down explicitly a basis of homology. In the same way, in cohomology, algebraic de Rham cohomology, we are interested to write down a basis of the de Rham cohomology. And in our main example of a affine variety, actually, we can do it. Maybe in some lecture, I will explain this one as a continuation of the Atiyah-Hodge theorem. But I think for today, it is we are done. And the next lecture, I was planning to show that the de Rham cohomology is algebraic de Rham cohomology is isomorphic to the classical de Rham cohomology. But I have changed my mind. The next talk I will talk about Hodge filtration, and in this way, as soon as the Hodge filtration is done, we can start directly talking about Hodge cycles and so on. Okay, maybe just